Hello, welcome back. So, in the last section of this chapter, we will look at the kind of problems, the kind of situations where we want to link motion of one particle to another particle. So far, what we have been studying was only motion of a single particle. And we looked at a bunch of different frames and how we can describe a single particle's motion. But often in our problems in engineering practice, we have some information about motion of one part of our system. We have some information how it is related to another part or another point in the system. And using this information, we want to infer the motion of the second point. There are two different kind of aspects to it. One is when there is some kind of physical connection, some kind of constraint between the motion of these two points of interest. And that is what we study here. That is the concept of dependent motion. Another concept is when there isn't such link, but still we want to use information about motion of one point to find the information about another point. And in that case, we can use the concept of relative motion and relative measurement between motion of the 2 points to try to infer this relationship and solve positions, velocities, accelerations of another particle. So we will look at these two concepts in these videos. First one, let's consider the case where there is a physical connection. Let me start by giving you an example. Consider one particle. In a very simple case, it is moving along a straight line track. So it's a rectilinear motion. Consider another particle moving along a different track. Again, for sake of simplicity of this example, both of them rectilinear motions, maybe in different directions. Now let's add something fun. Let's add a link between the two. So it could be like a rigid link, a piece of wood that links the motion of these two rollers inside their grooves. Notice that, for instance, as this one moves down, it pulls the rod. The other particle has to move along the track in a certain way. So the motion of the two particles are linked together. The question is, how can we use information about one of the points, like point 1, to infer information of the motion, to infer some information about particle 2. So there's good news and bad news. The good news is that these problems are usually very fun. I like to look at them. They feel like a puzzle. You want to move things around in your head, different relationships, and figure out how the motion looks like. The bad news is there's generally no one-size-fits-all approach that solves all the problems. Every problem is probably a little different, requiring a bit of thinking and possibly adjustment of your approach. And that actually adds to the fun, in my humble opinion. But anyways, here is our goal. We have one particle, motion known, find the motion of the other particle. We can be a little, at least conceptually, systematic. Let's assume I know some position S1, and I want to find another position S2. Let me write it this way. I have S2 and S1, if I can somehow relate the position of the second particle mathematically to the position of the first one, that is a very useful information, because then I can go and take derivative of S2 becomes d over dt of S1. So I can take these mathematical derivations to get to the positions and velocities and accelerations of the second particle. The main challenge is how do we find this relationship? And that is where there's no one-size-fits-all general approach. But we can follow some guidelines, at least to help us shape our way of thinking. And let's see what needs to be done. Let me clean up a little. So first step in any of these general problems is, let me write it down. 1, identify particles of interest. So in this case, I have already identified I have two particles, particle 1, particle 2. So I want to find the relationship between these. Step number 2 is probably one of the most important one. Establish some good coordinate frames. And when doing that, we should use our intuition about the physics, the kind of motion that happens. So here I have an example that as particle 1 goes down, particle 2 moves to the left. So in that case, when I want to establish the coordinate frames and the position coordinates, it is a good idea to take some fixed points. No, let's do it this way. And define position coordinates according to that chosen reference frame. So in doing this, we can find these let me write it. Coordinate frames. Let's call it positions from a fixed point. Fixed point. And I emphasize both from and fixed point. So we find some fixed locations in space and define our position coordinates from that to the location of the particle. Note that the fixed points location is locations, fixed points. Let me add another emphasis that they don't have to be same point from all particles. The fixed points could be, and usually are, different. What else I wanted to say? Fixed points, position from... Yeah, I don't remember. I think maybe that was what I want to say. So now that I have defined these coordinates, S1 and S2, number 3, the puzzle one, is identify the constraining quantity and in this case this quantity that is constraining the motion of the tool is the fixed length of this rigid rod. Often in many of the problems we have ropes, we have rigid links, we have grooves. So these kinds of relationships or quantities, angles, lengths, and so on are our constraining quantity. And the last one, maybe not last one, for write each constraining quantity as function of position coordinates. So if I want to follow this example, I know the constraining quantity is the length, and what I can do is, let's assume these two tracks are perpendicular to each other. I can write this L squared equals S1 squared plus S2 squared. Or maybe if I want, my interest is finding, no, let's keep it as is. So now I have a relationship between position coordinates and this constraining quantity. The next is optional. This is really what you need. You have now some function of S1 and S2 equals something, equals maybe 0. You can write it as minus L1 plus equals 0. You have this relationship, and you can take implicitly time derivative of this to get to the positions or velocities. Or alternatively, you can, if possible, not always possible, find the one that you're more interested in, S2 equals L2 minus S1 squared square root and now you have an explicit function of S2 equals some function of S1. But if you do that, sometimes it becomes tricky and kind of fun. Note that when you're taking a square root, both plus and minus are valid. And this is math. And math is absolute and correct. You have to be careful to interpret your math correctly. And in this particular problem, both locations of the particle in either side could be valid. So one of them positive, the other one negative. So it is up to you to interpret which side is correct. And finally, when you have it, you can take time derivatives to get to the velocities or accelerations. So when S is plus minus, let's take plus. When S is the square root of L2 minus S1 squared, you can take S dot 2, right? Yeah, 2. Equals, now I'm taking derivative on the final one, over square root of L2 minus S1 squared times minus 2 S1 S dot 1. So now you find a relationship between the positions, the velocities, and so on. You can take another time derivative to find the acceleration. I'm not going to do that. So the main part is really trying to find this relationship. And in doing that, often it makes sense to be systematic in how you define your coordinate frame and coordinates of the two points of interest. It is always helpful to consider a good fixed point from where you can define these positions. And if you're careful, probably the rest is relatively straightforward. So I think that is it. As I said, every problem has its own characteristics. So probably you need to adjust your thinking a little. We will see a bunch of examples in class. But the overall procedure, it roughly follows the same pattern. So I'll end the video here. And in the next video, we'll look at relative motion analysis, another way of relating motion of 2 points to each other, and that should be the end of this chapter. So I'll see you in the next video.